So hi, it's going to be a talk about my research, and it's going to be like an informal talk, and I'm going to talk about my research mission, what I'm trying to accomplish. I'm going to explain a little bit about opponent shaping algorithms. I'm going to show some results I got, and I'm going to talk about my next steps. So a little bit about myself. I made a little bit of a different journey than what I guess all of you have done. So I don't have any university degrees. I'm not in an academic program. I am an affiliate at Tufts University where I'm part of a lab there, but I'm not studying for a PhD or anything. I worked as a software engineer for like 12 years, and I worked on the research as a side project for fun, and it sort of became my full-time career. And I haven't mentioned, I'm interning with CAM. So I want to talk to you about what I'm trying to achieve here. So here's my research mission in 3 points. We want AI systems to have ethical values. Right? So some of these ethical values are, if you are deciding which person gets a loan for housing, you can't discriminate based on whatever. And also don't exterminate the human race and a bunch of other stuff. It's all pretty much like be a good person in a sense. Now, I am putting it in the term of ethical values because I think lots of AI safety research is more about how to prevent the AI from doing bad things, how to put sort of like guardrails, AI, provably safe AI system. AI can do something bad. I am thinking about how do I make AI a good person? How do I make AI not want to do bad things? Right, so that's point number 1. Point number 2, that's my observation that ethical values are a social phenomenon. And when we think about what being good means to us, it usually comes from lessons, experiences that we've had with other people, right? And so ethical values exist within a society, within a social group, and a social group has to have ethical values in order to succeed. It has to have the people sort of caring for each other. I'm pointing this out. It may seem like an obvious thing to point out, but so much of the alignment work is like, let's take a single LLM and align it. And it's just like a sort of solitary experience of a single system getting better data. So it can be argued that ethics don't work that way. Ethics are a multi-agent phenomenon. And the third and very, very simple point, maybe if we get agents to learn how to behave socially, they're going to learn how to behave ethically as well. Maybe it's just something that comes along with the territory. Yes, and this is a good time to say, feel free to interrupt me with any questions that you have.
So if you have a sort of multi-agent AI system and they sort of evolve sort of a kind of ethical values amongst each other, couldn't it happen that the sort of ethics they have is about protecting each other, but not necessarily other humans?
Yes. Okay. Yes. I mean, right now, that's something I'm going to talk about, but right now we can't even make, like when we talk about multi-agent agents, we can barely make them have any ethical values, not even those we agree with. So we do have to understand that like, there are many ethical values that we don't agree with. We want them to have the right ones, but we're not even at the phase of choosing the right ones, as far as I'm concerned. We're at the phase of, we don't even know how to get them to have the wrong ones.
Mm-hmm. Right.
Let's talk about ethical rules and also some we don't agree with. So I'm just throwing a few random ethical rules out there. Honor the father and mother. It's a classic. It's another big one. They're gonna get more challenging as I move on. Here, don't speak your native minority language in public spaces or schools. So I intentionally chose one that I think most of us are gonna disagree with, and I had a few other choices for controversial ones, but tone it down. So my point was exactly the point that you're making. When we talk about what is an ethical value, it doesn't have to be one that we agree with. Right? Many ethical values that we don't agree with. And here's the curveball: don't eat bacon. So that's a rule. I think for most liberal-minded people, a rule like that, whether you agree with it or not, isn't even ethical. Isn't even an ethical issue. More like a dietary, religious preference. I do think that for most of the more conservative religious people in the world, which is most of the people in the world, it's the same family of rules, right? I've been breaking this rule a lot since I came here. No, I'm not like that. I've been breaking all of these rules except that number 2. even though my contract with Barry says I'm not an employee, so I guess I don't even have number 2. Yeah.
I'm a bit confused because are we talking about values or are we talking about rules? Are we talking about intrinsic?
I guess you could make a distinction. I'm not making a distinction. I guess you could say there is an ethical rule when people phrase it out in an explicit way, And there's a value, a lexical value that are more like a vibe, but I haven't made that distinction here.
Okay.
Let's talk about some work into social behavior of AI agents. So I'm going to talk about LLMs and reinforcement learning and a bunch of other stuff. I guess most of you have seen this work from a couple of years ago, where
Sorry.
that's perfect ringtone for yeah, I guess most of you have seen this work, the simulacra paper, Generative Agents, Interactive Simulacra of Human Behavior from a couple of years ago. They basically got a bunch of LLMs to interact with each other in a sort of virtual village. I guess this is maybe Pokemon inspired or some other video game. They got a bunch of LLMs to sort of play act that they're in a village. Each LLM is a character. They have a bunch of events going on, and they have sort of like social intrigues happening within each other. Like, hey, Klaus, mind if I join you for coffee? Not at all, Abigail, how are you? And I'm not, so this is not what I'm going for. And, there are some people who say that LLMs don't really think, they just imitate, they're what we call stochastic parrots. And I'm not one of these people. I think it's a really difficult question to say when an LLM is imitating and when it's actually doing things, and where does the line go between imitating and actually doing the thing? Here, I'm getting a very strong imitate vibe. Like, an LLM is going around talking about coffee, and an LLM has never experienced coffee. Like, I'm not looking for an LLM to do an imitation of what human experience looks like when you write it in text. I'm looking for something that's a little bit difficult to define, but it is, well, here's a point I want to make. We as people, so here in the previous paper, we basically had LLMs sort of try to imitate the social behavior of humans, like talking about meeting for coffee or a mayoral election. And as humans, we are incredibly socially evolved, and we usually don't think about how incredibly socially evolved we are. We kind of take it for granted. Even just, the fact that I can now look at you, there is eye contact between us, and there's some form of communication that happens when we have eye contact, stuff that we never think about, but it's there. We have like an entire stack of social mechanisms that we take for granted. And looking down at other animals that are less socially evolved than us, we can appreciate how big of an ivory tower we're on. I don't know, if you take like an animal like a dog, you see my cursor? Yes, you can. If you take an animal like a dog, it's not as socially evolved as us, but they do live in packs. They can give their lives to save other members of their pack. And and the level of development of AI agents, as I see it, I wouldn't even put it on this spider. I would put it on a single-celled organism. I mean, in the sense of like the ability of an agent to truly understand that it's interacting with another agent, and the other agent is not just a part of the environment that's making sounds. It's an actual thing that's somehow different than just plain environment. Like I feel that we're not there yet, and I want to slowly climb up that ladder. That's my goal. I want to show you this video from 2019 by OpenAI. I guess most of you have seen it. We've only going to watch a couple of minutes, but that's a video that does sort of like, and I'm again speaking intuitively here, give me that sort of spark of I'm looking at something alive. I'm looking at something that is somewhat of a real social behavior. So let's watch a couple of minutes. You have a question? Oh, let's watch a couple of minutes of that. Oh, okay. So I guess I'm going to dub over it. Okay, so basically it's an RL setup that they've got. They have hiders and seekers that are playing a game together. The red agents are the seekers and the blue agents are the hiders. And they've made it pretty for the wide public to enjoy the video. And they're training these two teams against each other in a game of hide and seek. And they've got they got different tools and different setups here, and they're learning using RL, and they're gradually learning different strategies to beat the game. So the blue agents can now lock boxes, and they are building a shelter for themselves to protect them from the seekers, from the red agents. And now they've provided the seekers with a ramp, and maybe in the next episode. Yeah, the seekers learn to use the ramp and then catch the hiders. And then the hiders learn to hide the ramp, so the seekers couldn't access it. I really love this video. I think like in multi-agent array, I think it's the favorite video I've seen. And then there's going to be like a couple of other cool things. Let's wait for that. Oh, they can also build a shelter out of walls. Gonna take a while doing it though. And the coolest thing they've shown is that the seekers sort of like found a sort of bug in the game rules that allow them to surf on boxes. They're gonna show that now. They get on a box with a ramp. Like it puts the box next to the ramp, gets on the box, then the surfs on the box to get to the shelter. And in the later stage, the seekers learn to lock the boxes to prevent that from happening. So that's very cool. And it does give me, again, intuitively the feeling that there's something alive in there, which I like. So the things I like the way that the agents work in a team here. I don't like the way that the teams are predefined. So like the agents sort of like born is either blue or red, and they are trained based on the success or failure of their team. So they get a reward signal as a team. They're trying to get the team to win. There is no conflict between the individual and the group. Right? So for us in teams in real life, right now, like we're a team. We were not born a team. We were put on this earth and sort of like made reward functions for ourselves. Like the team building activity that we do as people, that's the amazing thing that I want the AI agents to do. I don't want the teams to be built for them. So that's what I'm going for. I could talk here about agonistic democracy, which is the school of thought of you like that?
Cool. Yeah, I'm a big fan of agonistic democracy.
Cool. I won't get into that because I prepared way too many slides that I want to have time for, so we could talk about it later. Let's talk about so like, okay, let's say we want AI agents to behave more socially. Where do we even start? There are so many sort of social mechanisms and skills that we use as people. So some of these I've listed just a random list. Some of these are people use, some of these are also animals use. Where do we even start? And when I think about where to start, I think about this old game. I don't know how many of you played Civilization 3 back in the day. So in this game, you sort of like, you play the civilization and sort of try to win out and be as strong as possible and get from the Stone Age to the Space Age. And this is not historically accurate. Yeah, but I think. But I like this because it's like showing like a bunch of different technologies and saying, oh, you want construction, you want this technology, you have to figure out a bunch of other technologies too. So all of those skills are arranged in a directed acyclic graph. And you're playing the game of unlocking the skills that you know on the way to the skill that you want. So when I'm trying to think how that would look like for AI social behavior, I'm thinking, I want to get here. I want to get to AI agents behaving ethically. I'm unlocking stuff here. I want to unlock the thing that's going to unlock as many other things that's going to get me to ethics. And the one particular social mechanism that I've been obsessing over for the last 3 years is reciprocity. So reciprocity is meaning the behavior in which if someone is good to you, you want to be good to them back. Right? So it's a basic behavior of humans and animals. And I think it's the one that interests me the most because no human social behavior works without it. And it is simple, and AI agents are not good at learning it. So that's why I became so interested in it. And I've been reading all kinds of papers trying to sort of produce reciprocity or at least cooperation. And I didn't like almost all of them until I found opponent shaping, which I feel is the most profound solution for reciprocity. And I'm going to talk about that later. So they've accomplished reciprocity, and I want to use that. And the first box I want to unlock with reciprocity is a phenomenon that I'm going to call team formation. I want to put, it's basically what I was talking about before. I want to put a bunch of agents in the same environment, let's say 10 agents, and I want 3 or 4 of them to sort of say, let's work together. You, me, and Agent 7, and maybe Agent 9, we're going to be nice to each other. We're going to do things that benefit each other. We might not do things that benefit other agents. Then we'll have some way of communicating or identifying ourselves to each other, but we're going to help each other. We're going to be this little block. That's what I want to accomplish, and I've been working on this goal for like 1.5 years. And I'm hoping that reciprocity is going to generalize to team formation by way of transitivity. If you have Agent A and Agent B that tend to be reciprocal with each other, and agent B and agent C that tend to be reciprocal with each other, and they maybe identify each other or decide to be reciprocal based on their behavior, then maybe they behave in a way that's similar enough that agent A and agent C will also tend to reciprocate with each other. So that's a sort of like intuition that I have for why this would work. By the way, I've been talking a lot. If anyone has any questions, feel free to interrupt me.
So can you define transitivity again?
Oh, transitive is like for a relation, if A is related to B and B is related to C, then A is related to C. I mean, it's a math thing, not really.
Yes, I understand that much, but what is the thing that is transitive? What is the relation?
Oh, the tendency of two agents to be reciprocal with each other.
Okay. Okay, so in this case, A and C would be reciprocal?
Yes.
Okay.
I mean, that's just an intuition, though. In different environments, it could be transitive or not, or partially transitive. Yeah.
Did you consider also indirect reciprocity?
Indirect, what do you mean?
So in evolutionary game theory, reciprocity is one of the mechanisms that actually gives you cooperation, but this is only by having direct contact with whom you're playing. But you also have indirect reciprocity, where you can actually observe others, and based on what you think is good and bad, because we're talking about norms and ethics, you evolve behavior and you will cooperate with those that actually act nice with other people and actually are acting nice to other people, for instance. And there are these kind of rules that evolve from these strategies that actually allow you to get sustained cooperation, not by direct interaction, but by observing interaction between others in this kind of context. So I think it maps with what you're trying to do here, is to have this kind of indirect effect. And you say A cooperate with B and B cooperate with C, so I want A to cooperate with C. So this actually links a bit to this kind of theories that you have.
Right, I see.
I will show you later if you want.
So the simplest way to moderate, sorry, I forgot you.
Are you thinking of reciprocity as intrinsic, as like they've been selected over time for like they do better if they act reciprocally and then they get selected for that, or more extrinsically as in they can just like see the game tree, they know, all right, I don't actually care about this other person, but like it'll be to our mutual benefit if we cooperate.
Oh, I'm not sure I can tell the difference between the two options that you gave. I do want them to learn reciprocity because they conclude it's better for them. I don't want to sort of like, I don't want to, give them a bonus for being reciprocal because I don't think that's the way to go. I'm not sure I can tell the difference between the two options that you gave though.
So I might think that like intrinsically I'm like reciprocal with my family because evolutionary dynamics have like shit. So like I inherently care about my siblings, sort of like, and maybe my brother is like a ne'er-do-well and always defects, but I still have sort of the like, I keep on trying to act or like well towards them because I'm expecting reciprocity, even though I might mentally know that it's not going to happen.
I think I kind of understand. It's really a philosophical question because it's really difficult to put the line between those two behaviors. But the algorithm that I use, and I'm going to show you, opponent shaping, it does make them reciprocal. Actually, you know what? I'm not sure. Let's stay with that. Yeah.
How does an agent decide to be cooperative with the other? Like if I met a new agent I've never met him before, how do I decide if I'll cooperate with him or not? How do we create the first link?
You've never met before. How do I decide? Really depends on the environment. I think I should show my environment, then we'll talk about stuff like that. So the easiest way to demonstrate reciprocity is the tit-for-tat strategy in iterated prisoner's dilemma. Does anyone want a refresher on IPD? Yeah? Cool. So IPD is one of, I guess, the most famous game in game theory. It is a two-player game. It's a game that in each player has two possible options, defect or cooperate. And the best possible result for both agents is if they both cooperate, which is this result. However, they are both tempted to defect, both because they get a higher number of points if they do, and also because they are afraid that the other agent is going to defect and get the 5 points, and then they're going to get the 0. And then both of them end up defecting and getting 1 if they play the game just once. So they have two motivations to make them defect, which is greed and fear. And when the game is played multiple times, we call that iterated prisoner's dilemma, and then you get such interesting strategies as tit for tat. An agent that cooperates on the first turn, and then on each turn does what you did to him on the first turn, to it. And that is a very strong strategy. It is a very simple strategy, but it is resilient to being taken advantage of, Because if you defect to it, it's going to defect back. It's not a sucker, but it tends to cooperate with cooperators. Okay, so let's start with a little warm-up. Here are results from two reinforcement learning agents playing iterative prisoner's dilemma with each other. I'm measuring their cooperation rates, so it's going to be 1 line per agent. I'm measuring how often they tend to cooperate. So I want you to try to guess with yourselves what these 2 lines are going to look like. Yep, they look like this. They both learn to defect. I should have also put what?
I'm surprised, actually.
I should have also put another plot here for the reward. The reward also goes down. So it's like they're both optimizing as hard as they can, and their reward is going down. Interesting. The interesting thing about tit for tat is that it's like tit for tat is such an incredibly simple strategy, and reinforcement learning are not able to learn it. Like they can learn how to beat Go and chess, which are incredibly complicated. But there's something about the tiny, it's like a tiny little step. It's like a Roomba that can't go over a step, no matter how tiny it is. It's like it requires a sort of like leap of faith, or I don't know how would you call it, that our algorithms just can't do. Because I mean, try to think of yourself as an RL algorithm optimizing your behavior. I'm going to be a little bit. I mean, what do? They sort of like check in which direction. If they move a little bit, they're going to get a little bit more reward. So what? I'm going to be a little bit reciprocal. I'm going to cooperate on the first step. What's going to happen then? Other guy is going to defect. I'm going to answer cooperation with cooperation. What's going to happen then? Other guy is going to continue to defect because they don't know reciprocity. Yeah.
I see the point that you're trying to make, but I think there's an important distinction between Go and IPD. That's zero sum, and that's not.
Let me think about that. I mean, there is that difference there, but I'm not sure that even makes. I'm not sure that this makes a difference.
Aren't they both zero sum?
I need to think about it.
What do you mean it doesn't?
I mean, she's right. Go is zero sum and IPD is not. However, I think that it's also possible for our algorithm to succeed in non-zero sum games, but there's something about reciprocity that is the challenge for them.
And the point is that just training agents that solve general sum games is harder.
Well,
Training agents that solve general sum games is like harder than training agents that solve zero sum games.
Sorry, I can't make out the words here.
Training agents that solve zero sum games,
yes,
is just much easier than training agents that solve general sum games. Just for like various reasons.
Because just to add to that, like to train Go, like self-play technique in zero sum games is fantastic, but you can't use self-play in general sum games. That's why there's a huge distinction between these two.
Okay. Sorry.
So I would just say like both of them should be the buff dog, because the thing that you want to learn in the prisoner's dilemma is to reach the equilibrium. Or sort of like what you're trying to say is like the good outcome isn't the one that we're training for, rather than the training method isn't working.
Yeah, again, that's a philosophical question about what the agent wants, like what we want the agent to want. Go ahead.
I was just wondering, did you ever try like just training one agent? And as like we have 2 separate agents, right?
Yes.
I was wondering, like, if you trained only one agent but it's playing itself, what would happen?
I did try that, and sometimes they learn to cooperate. It's not very interesting to me. You know, it's not social behavior. It's like behavior towards a mirror. I want to talk to you about opponent shaping algorithms. So I know at least a couple of people here have been sort of flirting with them. So I'm going to explain what they are. So opponent shaping algorithms, the people who developed them, I think did the most interesting advancement in getting to agents that act with reciprocity. And the first paper was LOLA, Learning with Opponent Learning Awareness. Basically like a reinforcement learning agent that is aware of the other agent's learning process. So if let's say a normal reinforcement learning agent, it's called the vanilla reinforcement learning agent, if we personify its equation, sort of asking, how do I change my behavior so I could get more reward? An opponent shaping agent is asking, how do I change my behavior so that the other agents will learn to behave in a way that gives me more reward? So we are differentiating theta 2, or like the effect of theta 2 on something, with respect to theta 1. And these agents can sort of think, how do I behave? How do I maybe educate the other agent, or shape it, to use their actual terms, to do what I want? So you might be looking at this and thinking, how the hell do you differentiate this with respect to that? It looks like hell. Yes, it is hell. There are a bunch of papers about how difficult it is and how we can make it a little bit simpler. And the paper that's the most interesting to me is the advantage alignment algorithm, which was just presented at the iClear. And what they've done is that, I should have actually added more equations for them. They basically added the assumption that every agent is always assuming that the opponents are doing Q learning rather than a policy gradient, which really simplifies that gradient. And when they assume that, and they do the derivation, their final result is this. This is the equation for advantage alignment. Now, it took me 2 months to understand this equation, so don't feel weird if you don't understand it immediately. And here's sort of like a breakdown of this equation. So this is the part that the agent is optimizing. This times the log likelihood of the actions. This is the vanilla RL advantage. That's what you would have in a normal reinforcement learning algorithm. Oh, maybe I should say what everything is. This is the state, current state, action of agent 1, action of agent 2. And this, I guess you could call it the added line advantage. This is the regular vanilla advantage of agent 1, like how much better is the result it gotten from this action than what the result it usually gets in this state. And this is where the magic happens. This is the term that causes the agents to be reciprocal. I'm going to show the result of this in a bit. And it's basically, what have you done for me lately times how nice I am being to you right now. And they have a whole derivation for that, but basically it's, let's look at all the time steps leading up to now, and let's look at how, whether your actions happen to benefit me more than usual, and let's look at whether my action right now has benefited you more than usual. Even if both of these things are positive, then let's do this action more. So that's a really short explanation, but that's the gist of it. Let's see some results with this algorithm. And here are two opponent shaping agents playing iterative prisoner's dilemma, same game as before. So interesting stuff. And we are plotting their cooperation rate, how often they cooperate. So it seems like they do go through some things, and then they oscillate. And I was curious why they oscillate. I'm going to talk more about that later. And I also measured their reciprocities. I came up with a metric of reciprocity, which basically measures how similar to tit for tat they behave, like how likely they are to answer to cooperation with cooperation, and vice versa. And they both go very reciprocal, very fast, which is, I'm happy about that. Here's a couple more results. Here are 6 agents playing Prisoner's Dilemma. And I do have to explain a bit here because Prisoner's Dilemma is a 2-player game. They're playing it pairwise, meaning on each episode, they get paired in random pairs. They play with the same opponent. And then on the next episode, they'll be paired with a different opponent. And they also oscillate, and they sync together in the way that they oscillate. And I also plotted the reciprocities, and they all go pretty high, except one that takes a while to get together. What was the next thing? Oh yeah, and I also wanted to show just a glimpse of a different environment that I'm using. But I'm going to go back to IPD later. So I've also been experimenting with the grid world environments. So this is an environment I developed in which 2 agents move around in a grid world, and they can eat food, and they can eat. There's food that one agent likes and the food that the other agent likes. And so in a way, it's a proxy for Prisoner's Dilemma because it allows them to be nice or mean to each other, but not in a single action situation. And I'm going to skip over. No, I'm going to show this one. I got this result by cheating, but I still like it. So I was planning out, okay, it's like part of my goal is to design an environment in which agents will form teams. So I designed an environment that was cheating in the way that it was really encouraging with rules that are tailored to form the teams. And I made this nice code that visualizes the way that teams are formed. So later I can use it when I'm not cheating. And basically, they got the logic of each node here representing an agent, and each edge representing how nice that agent is to any of the other agents. And that way, I can sort of like see visually, like we've got something like 2 teams forming here. So now I can use this visualization to sort of look at the population and see how much they are forming teams. And the thing, okay, go ahead.
Just one thing, we are about at time, so
Completely?
It's
yes,
almost done, I guess.
but also it's like I mean, just people can leave if they want to, but
Okay.
I'm interested.
So I'm going to go for 2 more minutes. I'm just going to rush through it, okay? This last month, I've been sort of investigating why those agents are oscillating. And I discovered a couple of bugs, and I ruled out a few things, and I was really trying different things, different metrics. One interesting thing I've done, and I don't think, I mean, it's possibly it's kind of novel, is I separated the gradient to 2 gradients, vanilla and shaping, and measured the contribution of each of them to the agent's behavior. And so that the oscillation was caused by the shaping gradient rather than the vanilla one. So this way of measurement and doing this kind of derivative is kind of new. Maybe like I've shown this to people and they said it looks right. We've never seen it before. We hope it's right. I know. Found another bug, fixed it, had somewhat of an explanation for the oscillation. Going fast real good, aren't I? Mm-hmm. And after fixing the bug, I am seeing a slightly different oscillation. And I am seeing that one agent is always getting a little bit more reward than the other agent. And when I look at how often they tend to cooperate back when the other agent is cooperating, I see that one agent is always cooperating back and the other one is the one that's oscillating, which means that they have something like a dominance relationship, which is what I studied in my last paper, so I'm excited to find that here. So I'm planning on investigating that a little bit and understanding why there's a dominance relationship there. So the next things for me, investigate the dominance relationship, design an environment in which agents end up having showing informations, get into form teams, analyze the results, and write a paper about it. That's it. I'll be happy to answer any questions. Thank you very much. Yeah.
So in deciding how to play, they only take the previous actions into account, right?
I made this configurable. So in the examples I've shown here, they're only taking the other agents, the very last action into account.
Yeah.
But it's a hyperparameter. So sometimes I let them see the last 3 actions. Sometimes I also let them see their own actions, which is useful because you can sort of think it's like, okay, this guy's being an asshole to me, but I was just an asshole last turn. So let's even it out. Let's say we even,
Yeah.
Because otherwise they could get into infinite defection cycles. Like this is basically what's happening here. It's like they have a high reciprocity, but as soon as one of them defects, they just keep retaliating endlessly until the end of the game.
Is there any stochasticity in terms of making a decision, or it's just like always the greedy?
Well, they're policy gradient algorithms, so all of the decisions are stochastic. The environment is not stochastic. This one's not.
Do you ever try, adding some noise maybe to the they tried to cooperate, but the noise made it defect by accident.
Yeah, I experimented with that in the past. It's been at least 6 months since I used that argument that I added for the noise. I don't remember any distinct effects that it had. I mean, I've added so much parameters that now I can run like 1,000 experiments, which is cool. But now, so I've spent the last month investigating that oscillation, and it was interesting, and I learned a lot. But I'm also feeling a little guilty and a little worried that I'm working on obsessing over this thing, and I need to be working on the paper. So I'm kind of trying to wrap up this obsession soon and get to the actual designing of the environment that I want.
I feel like maybe noise might fix the oscillation, for instance.
Yeah, it's possible, yes. But then again, when the agents can look 3 turns back, which sometimes I've done that. I mean, while it's not technically noise, it just does increase the number of observations so much that it's not exactly randomness, but it's making the game a little more random-ish. Yeah.
So in the formula, you're using the formula you showed, right, to decide what action to take. Wait,
so please repeat what you said?
So the way you decide what action to take is based on the formula of this paper, right? This 2025 paper.
Yes, let me go back to that equation. Yeah,
that one. So can you play with actually, because I'm seeing 2 parameters, beta and gamma over there,
yes.
and so how does that influence your results? And can you play with having either one of them? So either only having the what have you done for me lately, or how nice I am being right now to you, actually trying to separate the effect of both aspects on your results?
Okay, I'll answer that one by one. And the gamma is just the discount factor for the environment.
Mhm.
The beta is the add-a-line factor, like how reciprocal you want your agents to get.
Mhm.
And if I run it with 0, I basically get an RL algorithm.
Mhm.
So I have played with it sometimes, a little bit more, a little bit less. There is no logic, I think, I mean, these two things come together. I mean, I haven't even considered breaking them apart because you only care about the relationship between them. You don't care about them individually.
Okay.
Yeah, I do think it's quite crucial because kind of the point is like if the A1 sum is positive, it means the other person has been nice to me. So then I want the sign of A2 to also be positive.
Yeah.
So I'm nice back, and similarly the other way around. So I would agree that it's kind of essential to have both.
I just wonder in this equation, do we not need to look at A2? We only have the time now and not the time in the past. And it's like, why don't we look at the time in the past?
Because this is about the decision you're making now.
Yeah.
Like it's the AT, it's the one that you're considering to make now.
But I guess like surely like for tit for tat, it's like what have you done for me lately is also like what did I do to you at the time, right? Like why do we and it's like we look at the past for.
But that's in the K, right? That's in the K term. So the sum goes of K smaller than T. So if you, I guess you have only one step before you were saying, right? So it's T minus 1 to T. So it's only T minus 1 in the sum, right? So when I asked you, how many steps do you look in the past? You said that only the previous.
No, wait, no. That's an important distinction. The observation is usually, for the examples I've shown, only one step in the past. But this is not the observation. This is the learning rule. And in this case, they're learning from the start of the episode. So this learning rule does not directly influence their behavior.
Okay.
It changes their parameters, but during the game, they cannot see more than one observation back.
Okay.
But because of the way the gamma is here, it really prioritizes the recent states a lot more than the old states.
No.
This is kind of silly, but if you could remind me, like I guess what advantage exactly means? I'm trying to understand why. What have you done for me lately? Like why is it what you have done for me? Like how do you associate it?
Yes, it took me a couple of months to understand it, and I can only partially explain it. But wait, like the concept of advantage, do I need to go for that?
Yes.
Yeah. Okay.
Just quickly, yeah.
Yes. So advantage is used in RL generally, not just in opponent shaping. It basically means how much more did I earn by doing this action now than I usually earn when I'm in this observation.
Based on some like current policy?
Yes.
Yes. Okay.
Yes.
Is it like Q minus B or something? Like,
yes.
Yes. That's what I'm remembering now.
Yes. And I was confused about this when I was looking at it at first, because I was thinking, because advantage two in a way is like the question of how well did agent 2 do?
Yeah.
Why do I care? Why do I care how well it did? Like if it happened to make a good decision, how does that influence me? But that's the part, like whether it did a bad decision or a good decision, that's the part that cancels out here. And the part that does not cancel out is whether I happen to do something that benefits agent 2. And I'm not sure I have the words to explain this.
I should look at it. It's quite interesting.
So like the part that doesn't cancel here is the component that I had. I'm saying I agent 1. I had in the success of agent 2, and the part that doesn't cancel out here is the component that agent 2 had in agent 1's success. That's the part that was tricky for me.
Yeah, now I want to see the math. It seems interesting.
And the entire thing here seems like it sort of like explicitly rewards reciprocity, but they got it directly from assuming that the other agent is doing Q learning. So they just did a long mathematical derivation that this was the end of. So I'm feeling quite confident that it's not. Oh, I would say it's like ethically neutral, in the sense that on one hand it can get agents to be reciprocal and nice to each other. It can also get agents to extort each other using strategies like ZD extortion, which you can say are a combination of reciprocity and violence. The reciprocity of you better do what I say or else, which is a sort of reciprocity. So I like the fact that the algorithms are ethically neutral, in the sense of like they're not biased. It's our job to make an environment in which they conclude they should behave well.
Oh, I have one more question. I guess this add-a-line thing is coming from this more foundational paper.
Yes.
the double gradient thing.
Yes, it started with Lola, then a bunch of papers, and then add a
Yeah,
line.
could you go to the slide with the gradient, the kind of double gradient idea? Yeah.
Yes.
So in the second gradient, so like it's kind of like a one layer deep kind of situation, right? Like the second gradient is thinking that theta 1 is fixed, like the original RL agent.
Or as in you assuming the other person is not doing the same thing that
Yes,
you're
yes,
doing.
yes.
Yeah.
And is there any like is that just fine? Has there been any analysis of that where it's like what if you went 3 layers deep? Does that change how you act? Is it okay to just assume the other person is doing normal RL?
Like assume that the other agent is doing opponent shaping as well.
Like another thing here might be some kind of like trying to do like a recursive thing. I don't know if that's.
Yeah, I think some of the opponent shaping papers have done that, but it was too meta for me.
It seems like already this is hard, so the other stuff might just be hard.
I would also think that it's a sort of a second order thing, right? Because already now because the step that theta 2 is taking is small itself, right? It's a small modification to theta 2. So you would get like a decaying effect of this. So it's that should just
I thought it was like it is at least like there's not some nice property where this is just complete somehow, but it's just like there's diminishing returns. I was wondering which case we're in.
Right. I mean, maybe, yeah.
I would say the biggest disadvantage or criticism of opponent shaping is how the hell do you get this to work on anything real?
That's right.
Like you got a bunch of like autonomous vehicles in the field. Like, hold on, I'm not gonna make this stop signal. I have to calculate the gradients of the Toyota in front of me. So like scaling in real world systems, it's not really clear how this would work. For me, it's not an issue because all of my agents are.
I think what you ultimately have to do is model the other agent, right, somehow, and then you can differentiate through your model.
Yes, MFOS, model-free opponent shaping, kind of does that. So there are some steps in that direction, but it is very, very challenging.
I mean, I think it sort of grounds out in some sort of like rule utilitarianism in the end.
Say again?
Rule utilitarianism or rule consequentialism. You end up, I mean, that's what the training produces, is a policy, right? You end up having a policy which has reciprocity embedded in it. You don't need to take you don't need to run the training every time you see another car.
Yes. Yeah, that's right. Okay, thank you very much.
Thank you.